Okay, so for the first one up here, we have to combine the powers on top first. When we're multiplying exponents with like bases, these all have a base of 10, so that means we can combine the powers. When we're multiplying, what do we do to the powers? Add them. So 10 to the 8th times 10 to the negative 5th, it's 8 plus negative 5, which is 3. When we divide now, oops, questions? When we divide now 10 to the 3rd divided by 10 to the negative 7th, what do we do with the powers? Subtract. What is 3 minus a negative 7? 10. So that's 10 to the 10th. Over here, we got 10 to the negative 6 to the power 2. When we have a power of another power, what do we do with the powers? Multiply. So negative 6 times 2 is negative 12. On bottom, we're back to multiplying here. 10 to the 3rd times 10 to the 10th. When we're multiplying, we do what with powers? Add 3 plus negative 10 is negative 7. Now we're dividing 10 to the negative 12th divided by 10 to the negative 7th. We are going to subtract. Negative 12 minus negative 7 is a negative 5. Anybody have both of the first two right? Cool. So, number 3 on top, 10 to the negative 5th times 10 to the negative 3rd is 10 to the negative 8. We're going to add the powers. On bottom, 10 to the negative 8 times 10 to the 4th is 10 to the negative 4. We divide 10 to the negative 8th divided by 10 to the negative 4th is 10 to the negative 4. Negative 8 minus a negative 4 is negative 8 plus 4, or negative 4. Over here, we do what's in the parentheses first. 10 to the 7th times 10 to the 4th is 10 to the 11th to the power of 6. 10 to the 66th.
I thought if it was a power, you'd have to take the times number, and it'd have to be 10 times 10 times 10 to get.
That's if you're expanding them out, but we're just trying to work with the powers without having to expand them out.
Oh.
We're trying to work with them abbreviated with just the powers. So now number 5, we do what's in the parentheses first. 10 to the 8th divided by 10 to the negative 7th. 10 to the 15th, yeah. 8 minus a negative 7 is 8 plus 7, or 8 plus 7 is 15. To the 3rd power, then, of course, is 15 times 3 makes 45. Then here, on top, first, 10 to the 4th times 10 to the negative 7th. It's 10 to the, on top, 10 to the 4th times 10 to the negative 7th. Negative 3. On bottom, 10 to the negative 5th times 10 to the 9th is 10 to the 4th. So you got the power negative 3 here. Now we're going to have to divide inside the parentheses. 10 to the negative 3rd divided by 10 to the 4th is 10 to the negative 7. Negative 3 minus 4 is negative 7. And then to the power of negative 3, 10 to the 21st. Any questions? Anybody get all 6 right? How many of you feel like you could do these if you had another shot at them? Okay. Just the last one's a little tough? I'll give you one maybe in the second hour class that's loads of fun. Why do we care? Why are we doing all this work with these powers of 10? Well, because we talked about scientific notation. And remember, we said our place values and our standard notation actually come back to these powers of 10. Now this is the ones place, but that's 10 to the 0. 10 is 10 to the 1. Hundreds is 10 to the second. 1,000s is 10 to the third. 10,000 is 10 to the fourth, and so on. And going the other way, the tenths is 10 to the negative 1. 10 to the negative 2 is the hundredths. 10 to the negative 3 is the thousandth. And so on going that way. So, when we had numbers we wanted to abbreviate, like 58 million, the focus was all on that first digit. That first digit is what really matters. So we take that first digit, we're going to put a decimal point after it to separate it from the rest of the number, so 5.8 it becomes. And what was the place value of that first digit? 10 to the 7. Right? Or if we had something like this, the focus was on the first, now I should specify, first non-zero digit, which would be the 9. So we put a decimal point after it to separate it from everything else, so it's 9.3. And what's the place value of the 9? 10 to the negative 5. That's where our scientific notation came from. But we came up with a shortcut. What was that shortcut? The decimal point starts here, ends here. What do we do? 1, 2, 3, 4, 5, 6, 7 spots. That's where I got my 10 to the 7th. I knew it had to be positive because this is a big number. And the positive powered place values are the big numbers. Same here. Decimal point started here, and we're moving it to here after the 9. It went 1, 2, 3, 4, 5 spots. That's where the 5 came from in our power. But we know it's negative because these are in the small, the negative powered place values are the small numbers after the decimal point. You guys feel okay with the converting, the scientific notation in the homework and stuff? Yeah? Okay. Well, we can review that a little bit more too as we come into it. What I want to look at now for just a minute is operations with numbers. Remember when we add or subtract, two requirements. Requirement number one, two things, two conditions. Requirement number one is we must have the same name. For whole numbers, we must be, comparing inches to inches or feet to feet or pounds to pounds. For fractions, it was a common denominator for adding and subtracting. For scientific notation, if I have something like 3.6 times 10 to the 7th, what part of that is indicating a place value? The 10 to the 7th is a place value. Because those powers of 10 are actually our place values. So to add two numbers that are in, add or subtract two numbers that are in scientific notation, they must have the same power of 10. The second condition, no matter what operation we're doing, we're going to combine the counts. But when we add or subtract, we keep the same name. So let's say I have that 3.6 times 10 to the 7th. And I want to add, now the parentheses around it are not telling me to do anything there. They're just saying that that's a single number. It's separating that out as a number all by itself. Plus 2.8 times 10 to the 7th. They have the same name. They have the same power of 10. So I can combine them with addition. When I add, I combine the counts. So the counts here are the 3.6 and the 2.8, which would make 6.4 times 10 to the power of, now a lot of people want to say 14 here. Why not? We keep, when we add or subtract, we keep the same name. So it stays 10 to the 7th. Just like if we had two ninths plus 4 ninths becomes 6 ninths. We keep the same name. We'll get to that. So let's say we have something like 5.1 times 10 to the negative ninth plus 3.6 times 10 to the negative ninth. Do these have the same name so we can add them?
Yeah.
Yes, they do. You guys tell me what to do to add them.
Add 5.1 and 3.6.
Add the counts. 5.1 and 3.6 makes 8.7 times 10 to the negative 9. The name stays the same. That is your answer, the way that is just written there. So in your notes, do this one quick. So we combine the counts. 4.9 and 3.2 make 8.1 times 10 to the 5th. Good. Doesn't always stay so simple. So 7.3 times 10 to the 8th plus 5.4 times 10 to the 8th. So we have the same name still, so we can combine them. So we're going to add our counts. 7.3 and 5.4 make 12.7 times 10 to the 8th. Good. Now, what's wrong with this answer?
The decimal point should be moved over.
Yeah, scientific notation only allows for one non-zero digit in front of the decimal point. So it can't have 12. It has to be 1.2. Well, we have to adjust our power of 10. Very good. Yeah, this number, to go from 12 to 1, it got smaller, right? Which means the power of 10 has to get larger by 1. So you add 1 to it, that's 10 to the 9th. This got smaller by 1 decimal point. This gets larger by 1 power. Basically, we divided this by 10, so we multiplied that by 10, is what is happening. So, (8.1) times 10 to the negative 7 plus 4.2 times 10 to the negative 7. Tell me what to do.
8.1 plus the 4.2.
Combine the counts. 8.1 plus 4.2 is 12.3 times 10 to the negative 7. Okay. We're just keeping the same name. 10 to the negative 7. So obviously we can't leave that as a 12. It's going to become 1.23. The number got smaller again, so the power has to get bigger. So it's going to be 10 to the negative 6. Yeah, we're adding 1. Negative 7 plus 1 is negative 6. A lot of people want to say negative 8 there because you're trying to go up, but you are adding 1.
Does the number of powers you add?
It's always the number of decimal places you move.
Okay. So
Yep.
if it's like
If it was 100,
123.
yeah. If I had 123.7 times 10 to the 13th, right? This time I've got to move it 2 spots here to make it smaller. I have to add 2 here. This got smaller by 2 places. That has to get larger by 2 powers of 10. So the question is, what if we don't have the same power of 10? Well, yeah, we have to make them the same power of 10. We have to give them the same name. Just like with fractions, where we renamed our fractions. When we're adding or subtracting, usually we'll go to the larger name. So the 2.79 times 10 to the 9th is not going to change. Over here, let's change the power of 10 first. This is times 10 to the 9th we want it to be. Did the power of 10 get larger or smaller? It got larger, so the number has to get smaller. This got larger by 1. This gets smaller by 1 place value. So that's now 0.93. I'll put a 0 in front of it. So now we'll add 2.79 plus 0.93 is 3.72 times 10 to the 9th. Make sense? I want you guys to try one in your notes. So 8.6 times 10 to the negative 9th plus 9.83 times 10 to the negative 8th. Try that one in your notes. See what you come up with. Let's see how you did. First, what power am I going to change them to? Which is the larger power? The negative 10 to the negative 8. So 9.83 times 10 to the negative 8 does not change. Over here, I make this 10 to the negative 8. What's the 8.6 going to become? 0.86. So now we'll add 0.86 and 9.8 is 10.69 times 10 to the negative 8. Are you done? No. What do we have to do? 1.069 times 10 to the negative 7. Yes, this got smaller, so the power has to get bigger by 1. So we add 1. Because you can only have one non-zero digit in front of the decimal point. You can only have one digit in front of the decimal point. So we had to move it over, so it was, instead of 10, it's 1.
Why would you change that?
The power of 10, so the number stays the same value. You can't just change part of the number. It's just like when you had 3/4 as a fraction. I can't just multiply the 3 by 2 to get 6 and leave this as a 4. That's not the same fraction anymore. I had to multiply the bottom by 2 as well, make that 8. So same here. If I change this piece, I got to change the name so it's still the same value. Let's look at subtraction. We might have 8.5 times 10 to the 8th minus 3.4 times 10 to the 8th. And just like with addition, we have the same name, so we can go ahead and combine. We're going to combine our counts. What's 8.5 times, or 8.5 minus 3.4? 5.1 times 10 to the 8th. Very good. So I might have 7.34 times 10 to the 13th minus 6.88 times 10 to the 13th. We subtract 7.34 minus 6.88 is 0.46 times 10 to the 13th. Is there a problem with that answer? Say yes. What's wrong with it? Got to move the decimal point. Yeah, there's nothing in front of there's a 0 in front of the decimal point. We have to have a non-zero digit in front of the decimal point. So it's got to go over. So this is 4.6. This time the number got larger, so the power of 10 has to get smaller. So subtract 1. So that becomes 10 to the 12th. So if I have 5.29 times 10 to the negative 9th minus 4.93 times 10 to the negative 9th, I'm going to subtract. I have the same names, 10 to the negative 9th. So 5.29 minus 4.93 is 0.36 times 10 to the negative 9. And again, we don't have a non-zero digit in front of our decimal point. We only have a 0 there, so we have to move it over. So 3.6 times 10 to the negative 10. Very good. The number got larger, power gets smaller. Negative 9 minus 1 is negative 10. Just like with addition, we sometimes might not have the same power. So I have 3.64 times 10 to the 8th minus 9.2 times 10 to the 7th. Just like with addition, it's generally easiest to change them to the larger power, larger name. So the 3.64 times 10 to the 8th is not going to change. This one's going to become times 10 to the 8th. So the power got bigger, the number gets smaller. Power got bigger by 1, number smaller by 1 place value. 0.92. So 3.64 minus 0.92 is 2.72 times 10 to the 8th. Not so bad? I'm going to let you guys try one. I'm going to have 1.34 times 10 to the negative 7th minus 0.97 times 10 to the negative 8th. Tell me what you come up with. Okay, well, let's see what you did here. Which is the larger power of 10? Negative 7. So it's the second one here that has to change. What's this number going to be? I screwed that up really bad, didn't I? That should have been 9.7. I'm going to stop and let you guys go from there again. So what's this become then? The power got larger, the number has to get smaller. So it's going to become 0.97. And then we'll subtract 1.34 minus 0.97 is 0.37 times 10 to the negative 7th. And of course we have an issue there. What is it? We have to make that 3.7. So the number gets larger, the power gets smaller. So negative 7 minus 1 is going to be negative 8. 10 to the negative 8. Anybody get that? 3.7 times 10 to the negative 8? Good. What's that?
Somehow I got it, but I didn't do it the way you did.
You might have changed them both to negative 8 first. That works too.
Oh,
Yeah. That can work. Let's look at when we multiply or divide. Couple of things when we multiply or divide. The first thing is our requirement. When we add or subtract, we must have the same name. When we multiply or divide, we don't need the same name. So that means we do not have to have the same power of 10. Second, as I said before, we always combine the counts, but when we multiply or divide, we also Combine the names. Okay. So if we have 2.5 times 10 to the 8th times 3.2 we're going to use times 10 to the 5th. Those have different powers of 10s. Does that mean I can't combine them? Oh yeah, we can combine them, right. So we're just going to combine the counts. 2.5 times 3.2 is 8.0 times 10 to the
Third.
we also combine the names, so 10 to the 8th times 10 to the 5th. When we are multiplying, we add powers, so 8 plus 5 is 13. So 4.1 times 10 to the negative 6th times 1.9 times 10 to the 12th. So we'll start out with 4.1 times 1.9. $7.79 times 10 to the negative 6 times 10 to the positive 12th. Negative 6 plus 12 is a positive 6. What do you think? You look frustrated. Is it making sense? You just making silly mistakes, or you lost? Okay. Time for a hard reset. $3.8 times 10 to the 9th plus, or times, sorry, 2.1 times 10 to the negative 11. Try that one in your notes quick. So we're going to combine the counts. 3.8 times 2.1 is 7.98. Times, we're going to combine the names. 10 to the 9th times 10 to the negative 11th is 10 to the negative 2. Good. Now, of course, it doesn't always stay that easy either. We can have 4.7 times 10 to the negative 6th times 5.2 times 10 to the 9th. Of course, we combine our counts. 4.7 times 5.2. There you go, 24.44. And then we combine our names. 10 to the negative 6 times 10 to the 9th. 10 to the positive 3, right? Negative 6 plus 9 is a positive 3. But we have two digits in front of the decimal points. This has to become 2.444. The number got smaller, the power gets bigger. This was smaller by 1 place value. That's bigger by 1. 3 plus 4, or 3 plus 1 is 4. Not so bad? No comment? Too tired to care? Let's look at, what if we have division? So I might have something like 2.444 times 10 to the 5th divided by 4.7 times 10 to the 12th. Well, 2.444 divided by 4.7. I'm going to divide the counts. What do I get there? I get 0.52. Then I also combine the names. When I divide exponents with the same base, both have the base of 10. What do I do with the powers? Subtract. So 5 minus 12 is -7. Of course, I'm not done. What do I have to do? That's 5.2. Number got larger. Power gets smaller. It's -8. So try 1.728 times 10 to the -6 divided by 1.2 times 10 to the 5th. So we divide 1.728 divided by 1.2 is 1.44. So now we also divide our powers of 10. 10 to the -6 divided by 10 to the 5th is -6 minus 5 is -11. Are we done? Yes, we are.
No. Come on, Evan.
It's okay. You'll be all right. Maybe. So let's do 3.456 times 10 to the 7th divided by 1.8 times 10 to the -9. So 3.456 divided by 1.8 is 1.92. 10 to the 7th divided by 10 to the -9th is 10 to the 16. Very good. What's that? Oh, sure. It happens. We won't hold it against him. So let's take 2.4 times 10 to the 5th divided by 9.6 times 10 to the 12th. Try that in your notes for me. So let's see what we get here. 2.4 divided by 9.6 is 0.25 times 10 to the 10 to the 5th divided by 10 to the 12th is 5 minus 12 is -7. And we're done, right? No, what do we do? That's 2.5. Number got bigger, power gets smaller. 10 to the -8. What do you think? Good stuff? Okay, I'm going to give you a little bit of time to get started on homework, and then we'll start talking again in another 15 minutes. We'll give you 5 minutes or so to work on homework. We'll take a break, and then we'll go back to her. In your book on page 130, exercise 2.6, looks like 59 through 81, the odds are operations with scientific notation.